Hi, I'm Chris, and I'm going to be talking about flexible approximate inference via stratified normalizing flows. This is joint work with my advisor, Stefano. So I'm going to give a one-slide overview of our project, then I'm going to go into a bit more detail about the problem setting, our method, experimental results, and then go back to the overview for the last slide. So what's the gist of our project in one slide? Well, we're trying to compute a high-dimensional integral of a function f over a space z. Now broadly, there are two ways to do this. Variational inference, where we form a global approximation of f and then use the elbow to get a lower bound. We could also use importance sampling, where we combine many point-wise approximations of f, which we evaluate at points we get from our proposal distribution. In our work, we interpolate between variational inference and importance sampling. We sample regions in Z, we then fit an elbow in these regions, and then combine them to get a tighter elbow overall. And we choose the regions intelligently by using a normalizing flow. So high-dimensional integration is a very common but very challenging problem. We see this in things like latent variable models if we're trying to marginalize out the latent variables. And more precisely, the setting is we have some function that we can query, we want to compute its integral over a space. I've already talked about importance sampling and variational inference. One interesting point is that they lie on opposite ends of the bias-variance tradeoff curve. Importance sampling is low bias, but typically high variance. Variational inference is typically the opposite, low variance, but high bias. Our method allows us to trade off between these two extremes. So we can see our method as a form of partition variational inference. We split the region, Z, into a set of disjoint regions, B. And what we're doing here is basically splitting the integral up into a sum of integrals over the subregions. In each region, we fit the variational distribution and then form the elbow, which is valid in each of the subregions, and so by combining them, we get a valid elbow overall. So why might we expect this to be useful? Well, if we have an f which is well behaved, then we might expect it to be smoother in the smaller length scales of the subregions, which means we can get away with using simpler variational distributions. Another point is that we don't have to exhaustively evaluate all of the regions. We can actually sample some of the regions randomly. This means that we can get away with using fewer of the regions, but in expectation, we still get our tight elbow. Of course, by doing this, we pick up some variance in the estimator we use. So how do we choose the regions to minimize this variance that we get? Well, we can imagine that if we chose uniform regions, we would have pretty high variance, especially as the functions f that we're trying to integrate are often going to be supported on some smaller typical set. So if we choose regions at random, uniformly, then a lot of these regions are going to have very low density of f in them. And so the estimator we have is going to be pretty high variance. Ideally, to minimize the variance, we want to have the elbows in each of the regions to be more or less equal. And if we fit the elbows well, then we get that if the actual masses of f in these subregions are equal. Now, we can use normalizing flows to choose the regions in a way that we satisfy this criterion. So in a normalizing flow, we get a bijective function from a base space to the objective space, which induces a density by mapping a simple distribution on the base space to the objective space. Now, one nice feature about this is that if we have regions of equal probability in the base space, they're then mapped to regions of equal probability in the objective space. This means that we can sample very regular regions in the base space, and then they get mapped to pretty complex regions in the objective space. We can see this on the schematic on the right. We have a two-dimensional example. We have a square as the base space for our normalizing flow, which we map onto a Gaussian. We've then shown 16 subregions or subsquares in the base space, which are then mapped onto the objective space. And as you can see, they're mapped to quite complex shapes in the objective space. So we can have very simple, regular shapes in the base space, which then get mapped to complex regions in the objective space. So how does the method work in a combined sense? Well, we can think of it as a two-step method. First, we train a flow to match the density of f. Then we sample a set of regions in the flow's base space, then optimize our variational functions in each of the sampled regions. Once we've done that, we can get the elbow, combine the elbow to get our tighter elbow overall. We also have a joint procedure where we can learn the flow and approximating densities parameters at the same time, but in interest of time, we won't get into that today. You can read it in the paper. So how does our method relate to importance sampling and variational inference? Well, in the limit of infinitely small partition cells, we show that we actually directly recover importance sampling. And of course, one very large partition cell recovers normal variational inference. So we can think of our method as actually interpolating between the low bias, high variance regime of importance sampling and the low variance, high bias regime of the variational inference methods. So we can actually choose the point along the bias variance trade-off curve that will fit our application the best. So does our method work experimentally? So we have some results on some synthetic data sets. This data set in particular is a very highly multimodal data set, a mixture of Gaussians, and we show that our method actually does better than the baseline, which is the same set of flows, but just using a normal variational approach instead of our sampling regions approach. Now, we expect that we would do better on multimodal distributions because we think that each region could handle a mode. And this would help the whole approach handle multimodal distributions pretty well, which historically flows have struggled at doing good inference in. So to conclude, we managed to interpolate between variational inference and importance sampling. We do this by splitting up the objective space into a set of smaller regions, each of which have approximately the same amount of density of F in them. And we do this by using a normalizing flow. We then fit variational approximations in each of the subregions and then combine them to get a better, tighter elbow overall. I'm happy to take any questions.